I'm Jacob J. Menson, and in this video, I'll be doing a brief overview of my moon return simulation. Feel free to stop and read the slides for more details, but I'm just going to be covering the surface level information. This project is based around a situation that I created, which is a NASA Orion inspired spacecraft orbiting in a polar orbit around the moon. My goal was to design and simulate a return orbit back into Earth. Step one was making a numerical integrator. I used 4th order Runge-Kutta, though in future steps of this project I plan on using Dormant Prince to maximize efficiency in numerical integration. I created this C++ class that would make the integration steps a lot easier and a lot more general in case I needed different sets of differential equations for different steps of the process, which I did end up needing and was very helpful. Next was force modeling. The moon position could have been numerically integrated using the sun and the Earth's gravity, but I figured that it would be a lot more accurate if I use NASA Horizons, which is a database that NASA provides that documents the position of the moon over time. The acceleration terms on the spacecraft is affected by the Earth and the moon. The Earth has a lot of terms here that take into account the oblateness, which means that the Earth is not a perfect sphere, whereas the moon is just a simple sphere, and the location is determined by the Horizons database mentioned before. So the differential equations were set up like this. There was 7 values of concern: x position, y position, z position, and then the following coordinates with velocity, and then lastly altitude. The 7 differential equations were given to the diffEqs class, which is xyz, velocity and acceleration, and change in altitude. This is an example of how the change in position, which is velocity, and the change in velocity, which is acceleration, were defined. You can read into this a little bit more if you want to see the details. So to estimate how this trajectory would start, I used the patch-conics approach, which is very simplified and not perfect given all of the variables at play here, but it gave me an idea of when to start looking for times to burn the engine. So you start with the transfer ellipse, which is the orbit from the moon to the Earth, or more specifically when the spacecraft leaves the moon's sphere of influence. I decided to go against the moon's direction. This is not optimal for delta V, but it just allows for more simple analysis since you're not going to be prolonging your effect under the moon's gravity. So after figuring out what the best transfer ellipse is, I calculated the hyperbolic moon escape. This figures out the delta V needed to get out of the sphere of influence and reach the speed that you need to go to the transfer ellipse that was calculated in the last step. Figuring out when to fire the boosters was a matter of the turning angle and figuring out what percentage of the period of orbit that you would need to fire your engines at. And this did not end up being perfect, likely due to all those simplifications I made before, but I'll mention that more later. So next was actually simulating the moon return. So it says here the delta V had to be changed to this value, and the time that the burn occurred was changed to this value. In the future, I plan on using propagation techniques that look at a bunch of different variables and vary them slightly just to find the best option. And I would use the values found before as like the center of where that span of variables would be. But in this first estimation, I just did this by hand. I found one that worked, and I'm just trying to build a foundation here for further analysis. So this is what the trajectory looked like for stage 1. Stage 1 being getting to the Earth's atmosphere. You can see here you're orbiting the moon, and then once the engines burn, it shoots up out of the plane and it comes in just barely not tangential with Earth's atmosphere. I decided to change it to be not in the ecliptic plane or almost the ecliptic plane because the moon is not in it either, because the velocity ended up being not quite enough. So having it out of line like this means that less of it's canceled out by the moon's velocity. Now we have hypersonic Earth entry. So the initial conditions were determined with a coordinate transform since I wanted to enter the Earth's rotating frame. This is some of the math that I did in MATLAB to get there. Now the differential equations are given here. This was taken from my aerothermodynamics class. This takes into account things like ballistic coefficient, which I talk about here. The ballistic coefficient models the aerodynamic performance of each stage of atmospheric entry. This is the variable that's going to be changed when the aerodynamic rules change when you go through different stages. Newtonian flow is how this is figured out for the hypersonic regime. Newtonian flow is an approximation that only works at hypersonic speeds. There's a lot of different rules for this, but at its simplest, you can assume that the coefficient of pressure maximum is 2, and for a spherical segment, which the Orion spacecraft is, and I used these measurements to approximate that, I ended with a CD found with this number, which I actually don't put in here, but it's in my MATLAB code. For the atmospheric conditions, I used a combination of the 1976 US Standard Atmosphere and the 1962 US Standard Atmosphere. I vary them at the altitude shown here. I defined another C++ class called FreeStream that takes in altitude and velocity, spits out a bunch of values that are used for further calculations. I made this for that same class, aerothermodynamics, where I did a lot with hypersonic trajectories. So this was a great tool to use in this project as well. I designed a user interface to make it a little bit easier to look at the data. I plan on making this user interface work for the entire trajectory, but since right now a lot of this was already developed for the hypersonic stage, it only really works for that part. The changes I made to this that are different from the class that I took is that along the way the ballistic coefficient changes to match the conditions of the atmosphere. And I'll go into a little bit about when that happens in the parachute. So it says here, the hypersonic regime ends around Mach 5, but for the sake of simplicity, I kept it going until Mach 1. And then at Mach 1, we're releasing the drogue parachutes, which is a stabilizing parachute. Doesn't slow it down all the way, but it gets it. It does a lot. Then the main parachutes shoot out. The estimations I used for both of these were from NASA's resources. The atmospheric trajectory simulation was the next step. I used that same UI that I referenced before, and here are the results. You can see the altitude versus time, velocity versus time, and altitude versus velocity. These little jumps happen when the parachutes shoot out, and this is, of course, fatal acceleration. But those are just estimations because it's a immediate change. The real fatal acceleration that is to be looked at is right here in the hypersonic regime. This would be fatal. It's a sustained 14 Gs during this portion, which is not suitable for human life. This trajectory could only really work for samples or a robotic mission. To fix this, you could use lift to stay in the upper atmosphere for longer, prolonging the lower acceleration seen here, or you could slow down, enter a low Earth orbit. There's a lot of solutions to this, and I plan to explore them in the future steps of this project. So let's take a look at the complete trajectory. We've got the first stage here, orbiting the moon. You've got the transfer up into Earth's atmosphere. You enter over the Indian Ocean, and you land here in the ocean. It took 5.3299 days and a touchdown at this time. So yeah, here's some things to improve. I mentioned a lot of these. I plan on adding the Dorman-Prince numerical integration method to my DiffyQs class. I plan to use more detailed aerodynamic models for the sub-Mach 5 regime. I plan to use lift to prolong the time spent in the upper atmosphere. I want to use Monte Carlo propagation to find ideal burn time in delta V. I want to determine a return orbit that lands in the Pacific instead of the Indian Ocean for geopolitical reasons. And I want to make a UI that compiles all of these regimes to find orbits and satisfy a set of conditions and mission requirements. So in conclusion, I learned a lot about numerical integration, applied orbital mechanics, hypersonic flight, and it strengthened my grasp of C++. I plan on really using C++ more in the future, especially making the classes that I used better, faster, and more applicable for these problems. All right, thank you for watching.